Good day. I'm Dr. Tim Floyd, Associate Professor of Mathematics at Georgia Highlands College, and this video is an introduction to functions. In this video, we will talk about the definition of a function. We'll use mapping to help us understand the definition of a function. We'll learn how to tell if an equation is a function by its appearance, and we will use the vertical line test to help us determine if a graph is a function. And in doing this, we hope you have a beginning understanding and maybe fill in some gaps on what is a function. First of all, let's have a definition. Now, you may have been presented several definitions of a function in your life, or what seem to be different definitions, but the main understanding is, the main pieces of the definition is that at its heart, a function is a relation. It is a set of ordered pairs, or something that creates ordered pairs, but we have a condition. And this condition is that no value of x, the domain value, no domain value can be paired with more than one range value or output value y. I have presented in another video the idea of a mapping. Now, let's say that I'm going to use a circle, and I'm going to use an oval actually, to represent values of the domain. I'm not going to use set notation. I'm going to use an oval, and we use another oval to represent values of the range. Now let's say that I have the values of -1, 3, -1/2, and 7 in the domain, and let's say we have 4, 3, -2, and 0 in the range. Now, if I create a mapping, what I'll do is I will just, and I'm choosing these, I'm not using a formula to create these, I'm just going to draw an arrow from, let's say, -1 to 4. I'm going to draw an arrow from 3 to 0, and from 1/2 to 3, and from 7 to -2. Now, in this case, if you go back to the definition of a function, we have no value in the domain is paired with two different output values. So if we look at this mapping, we see that -1 has a single arrow coming from it, connecting it to 4. 3 has a single arrow connecting it to 0, and -1/2, and 7. So in this case, if we were to write these, we could write these as ordered pairs then, and we would have a set of ordered pairs that would lead us to a function. And this then is a relation, and I know I'm repeating myself, but I want you to understand that because no value from the domain is paired with more than one value in the range, that makes this a function. So this would then be our set of ordered pairs, and set of ordered pairs makes it a relation, but then the fact that we have no domain value connected to more than one range value makes it a function. Now, let's make a different mapping then. So let's say that I have my domain little oval and my range oval, and let's say I have 1, 2, and -3 in my domain, and let's say we have 5, 4, 7, and 2. Now, and I'm just creating this because I want to make the example. Let's say that I have these arrows then, and then notice in this case then, if we were to create our ordered pairs, we have 1, 5, and if you notice, look at this picture and ask yourself, the condition for a function is, do we have a domain value connected to more than one range value? And if you will notice that the connection from 2 has two arrows coming from it. So from 2, we have a connection to 4, and from 2, we have a connection to 2. Now that is the only one that is happening with. The other two values are very nicely, simply connected to a single output value. But the fact that these two ordered pairs here have the same x value, or same input value, connected to different output values, that makes this not a function. So the mapping is a nice picture that helps us demonstrate that point. Now, if you have an equation or a function or a rule that creates your ordered pairs, then the key is that we have a formula or an equation so that we do not get two different outputs when we have an input. Now, I have written, and if those of you who may remember from your algebra life, that this is going to create a graph of a linear function. It's a line. And we're going to just use some thinking here. Not exactly a full proof of this, but I want to make a table, and I'm going to select some input, and we're going to create the output values. So let's say that I have x is -2. Now, if I were going to evaluate this, I would have -2 in for the input, and we would then calculate using our thinking or our calculator, and we would get a value of -9. You can verify that on your calculator. Now, any other answer that we might get from this by calculating this expression would not be a correct value, because the only thing we should get is this would be -4, and -4 minus 5 is -9. So an input, if calculated correctly, there is nothing in this structure that leads us to get a different answer. So by structure, and if we create another ordered pair, let's say we do 1, so we have this. In the same sense, no matter what value I put in for the input, let me finish that out, we would get only one answer. So in this case then, this formula and formulas like this, or equations like this, only give us the opportunity to get one output value for each input value. There's nothing in this structure that allows anything differently. So therefore, this is, in this case, the equation in this case is a function. By the definition, it creates ordered pairs, and the ordered pairs are made such that no input value can create two different output values. Now, in order to have a formula that is not a function, these are two of the typical situations that create this. These are not the only two situations that lead to a set of ordered pairs that would not be a function, but it's just two that typically we begin with. So in this case, let's say we have y squared equals x minus 3. Now, if you'll notice, the power that I have created, the even power, is on the output variable, not the input variable. Now, as we solve these then, let's put some values in for input. So let's say that I input 7. Okay. So I have y squared equals 7 minus 3. So we have y squared equals 4. Now, there are two possible values that I could square that will give me a value of 4, or give us a value of 4. So that's the way we have to think about this. We have two possible values. One of the values would be a positive 2. Because if we take a positive 2 and square it, we would get 4. Another value would be the negative of 2. Now notice I put the negative 2 in parentheses because I want, when we square this, I want to square the negative also. If you're putting this into your calculator, you must be sure to put the parentheses around the negative value for it to square it properly. And in this case, we also get a positive 4. So one input leads to two outputs. And there are every value other than 0 that we would put into this creates this situation. So y squared equals x minus 3, where the power, even power, is on our output variable, leads us to this not being a function. Now let me very quickly do one other example, and that would be with the absolute value. Okay, let me get my pen going here. Okay, so let's say that we have the absolute value of y equals x plus 3. Now, these are very short examples, but if this absolute value was on any of the output variables in the problem, then here's what happens. So let's say that I let a little short table here, I have an x and a y. So let's say that I have x equals 15. All right, so if we go to absolute value of y equals 15 plus 3, we get the absolute value of y equals 18. Now, here again, very much like with the even power, there are two values that gives us a positive 18. First of all, the absolute value of negative 18 is 18, and then the absolute value of positive 18 is 18. So we have, for 15 as an input, there are two possible y values, positive 18 and negative 18, that give us the same output value of positive 18. Therefore, by the definition of a function, we have a single input, 15, gives us two outputs, and this value and any positive number that we would put in would give us the same situation. Therefore, this, or any equation like this, would not be a function. Now, in each of these two examples, these are not functions, but they are relations, and that is okay. Relations are necessary. We just don't spend as much time on them as we do functions. Another way we can visualize both relations and functions is by a graph. And how do we then determine from a graph if the graph represents a function or a relation only? So let me make a curve on this graph. Now, anytime you have a graph in Math 1111, the important stuff is in the picture. Now, that might seem obvious, but this graph would continue going on, and there are no interesting things that happen in the graph as we continue on to inputs of onto negative infinity and positive infinity on the x-axis. This is the only interesting thing that is going on. Now, as we remember from beginning algebra, we have the graph is a line, but it's made up of points. Now, the points connect to some input values on, I'm just going to select a few here, just some random values. Now, In this case, if I pass a vertical line, so let me do it here. Okay. That line again passes through a single location on the graph. There's no part of the graph up here or down here. And I'm just going to let my red line, just imagine that we did this to infinity. There is no vertical line that would connect more than one point that is on this graph. Therefore, this graph is a function. And the vertical line test demonstrates that. Now, let's suppose we have a different kind of graph. Let's say that we have a circle. Now, the circle has locations that would be ordered pairs. So let's say I want to have the ordered pair for this location. So let me put my little dot right there and highlight it. So if we followed this, we would have -4, -4. So if I go on and write this, -4, -4, I have an ordered pair. So certainly this is a relation. Any location on the circle would create an ordered pair. But now here's the interesting thing. If I have this location, well, it happens to also go to -4, and it goes vertically to almost +4. So I'm going to say it's 4. It's not. If you look at this very closely, it's not quite 4, but let's just say it is. Notice, in this case, these two values are on the same vertical grid line. So we go to the same value of x, but we go to two different locations on the graph. So now if I use my vertical line test, we see then that this graph meets two different values of x. And in fact, any vertical line that I draw inside the circle, if I followed these grid lines or anything in between, all of these would intersect 2 points of the circle. So this is a relation only. It is not a function. And that is the use of the vertical line test to do that. I appreciate you watching this video. I hope it's helped you in your beginning understanding of functions, and I hope you will go on and watch other videos of mine or other instructors from Georgia Highlands College. We hope they help. We'd appreciate any input you would like to give us, and my email is listed on the video. So thank you, and I hope you have a very good evening.